All right, we are in the last section of this unit. This is lesson 7.8 on the chi-squared test of independence. A lot of material going to be covered here, so hopefully you're taking notes. We start with a contingency table, and those tables they compare two different variables. So in this case, I've got boys and girls in the rows, and then along the top I've got those who brush regularly, brush their teeth regularly, and those who don't brush their teeth regularly. And so I've done a survey of 400 boys and girls, and the totals are along the right hand side and along the bottom. So all of my data is there. So that's the data that I've collected, and that's how I start. Now I have a 2x2 contingency table, boys and girls, those who brush their teeth regularly and those who don't. So we are going to test for independence. We're going to see how independent it is between being a boy and a girl versus brushing regularly and not brushing regularly. So I want you to remember a long time ago when we were talking about probability, what it meant for two events to be independent. Well, what that meant was if those events were independent, then I could multiply their probabilities together and I would get the probability of being both. So I'm going to use that knowledge here and I'm going to figure out, well, if being a boy was independent from brushing their teeth regularly, then the probability of being a boy who brushes their teeth regularly would be the probability of being a boy times the probability of brushing regularly. So we're going to figure those out. We're going to do boys who don't brush regularly, girls who brush regularly, and girls who don't. So let's figure out the expected number of those 400 people. If there was complete independence, we're going to figure out how many of those 4 people would be boys who brush regularly, boys who don't, girls who brush regularly, and girls who don't. So I've already got the observed in the top table. So I'm going to take the 400 people, multiply that by the probability of being a boy, and multiply that by the probability of brushing regularly. So what is the probability of being a boy? Well, that's 215 of the 400 people. If you look at those totals on the right, 215 people were boys out of the 400. The number of people that brushed regularly was 209, so the probability of brushing regularly would be 209 out of 400. Okay, and that gives me 112.34. And I'm going to calculate the rest in the same way. So for boys who don't brush regularly, I'll take 400 times the probability of being a boy, which is 215 over 400, times the probability of not brushing regularly, which is 191 over 400, and I would get 102.66. And I fill in the other numbers the same way. So that's how many boys and girls I would expect to brush regularly and not brush regularly. I'm going to keep those values written down somewhere. So I calculate my chi-square. This is how I calculate it. I've got 2 tables, and in each table I've got the expected frequency and I've got the observed frequency of boys and girls who brush and don't brush. So I use those frequencies. And so what I'm going to do is I'm going to subtract the matching cells from each table and square that and divide it by the expected frequency from the second table. I'm going to add all that together, and that's going to be my chi-squared. Okay, so for each cell, there's 4 of them. I'm going to figure out my observed frequency, my expected frequency, and then I'm going to plug both of those into that formula. So for the top left cell, the 115 boys who brush their teeth regularly, I was expecting that to be 112.34. And so if I plug those into that formula, I get 0.06298. I do the same thing for the boys who don't brush. I do that for the girls who brush and the girls who don't brush their teeth, and those are the values that I get. Just looking at the last column there, if I look at the formula, I need to add all of those decimals up. So if I do, then my chi-squared is 0.2852. Okay? Now this is small, so gender and brushing habits are independent. It doesn't matter whether you're a boy or a girl. It doesn't have any determination on how likely you are to brush your teeth regularly. Now I say that this is small. We're going to talk about what it means for a chi-square to be small, because I can't just say, oh, it's small. So I need to know what values of chi-squared are small in order to say that those two variables are independent. So using technology, I can use my calculator, and what I do is I take my observed table, just the 2 by 2 numbers, just the values without the totals. I take that and I plug it into the calculator as a matrix, and in statistics mode I do a chi-squared test. That's what it looks like on a Casio. Okay, as you can see, there's the table that I put in with the 110, 106, 98, and 86. Then I do a chi-squared test, and there's the values that it gives me, the 0.217 and so on. Okay, and on a TI it would look much the same. Okay, so earlier, like I was saying, I said that our chi-squared was small. So what does it mean for a chi-squared to be small as opposed to big? Well, I need to look at two things to determine whether the chi-squared is small or big. I need to look at the degrees of freedom of my data. That's basically the number of cells in the contingency table that can vary if I know that the totals have to be kept constant. Well, the only thing that I really have any freedom in is putting in that first number, whether it was boys who brush, boys who don't brush. Once that first number is in place, the totals are going to determine what the other three numbers have to be. And that's true of a lot of tables depending on how many rows and columns you have. So the degrees of freedom is calculated as rows minus 1 times the columns minus 1, because once all of the numbers are in each row except for the last one, then that last one is determined by the total. Same thing with the columns. Once all of the numbers are entered except for the last one, then those are the only ones you have any freedom with. But the last one, the total, is going to determine what that last value in the column is going to be. So that's where that formula comes from. So we had a 2 by 2 table. That means we only have 1 degree of freedom. And like I said, that's the first number in the table. Once that's in there, the totals are going to determine what the rest of the numbers have to be. Okay. There's also a significance level. That's going to indicate what we decide is going to be the minimum acceptable probability that the variables are independent. And that's something that either we're told or we can determine by ourselves. Most people use 1% significance level, or 5%, or 10%. There are others that are used, but I think these are the only 3 that I need to concern myself with. So based on those two things, degrees of freedom and significance level, we can determine whether a chi-squared value is big or small. Okay, and so we have this table, and along the left you see the degrees of freedom from 1 to 12, and along the top we see significance levels from 10% to 5% to 2.5% to 1%. Okay, and so all you do is you line up the degrees of freedom that you have with the significance level that you want, and that's where your chi-squared has to be. If your chi-squared is larger than that number that you see in the table, once you line those two things up, then the variables are not independent. Okay, but if the chi-squared value that you get is smaller than that number that you get in the table, then the variables are independent. Okay? And then there's a third factor called the p-value. It's the probability of getting observed values that are as far as ours were from the expected values, or farther, assuming that the variables are independent. Okay? And we can get this on a calculator as well. When you do the chi-squared test, whether it's on a TI or on a Casio, you get that p-value. Okay? So here's how the formal chi-squared test for independence works. Step 1, we state H0. That's our null hypothesis, and this is a statement that the two variables being considered are independent. So we'll say such and such variables are independent, and that's going to be our null hypothesis. And then we're going to say H1, that's our alternate hypothesis, and that's the statement that the two variables being considered are not independent. Okay. So the rejection inequality, if my calculated chi-squared is greater than some k value, where k is that critical value that I got from the table, that's what I'm looking for. That's going to be cause for me to reject my null hypothesis. Then I construct the expected frequency table. I use technology to find my chi-squared, to calculate it out, and then I either reject my null hypothesis or I do not reject my null hypothesis, depending on the result of the rejection inequality that I calculated in step 2, once I figure out what my calculated chi-squared is. Notice that I don't say that I accept my null hypothesis. I either reject it or I do not reject it. Okay, and step 6, we can also use the p-value from our calculator to help us decide. If we are at a 5% significance level. If I get a p-value that's less than 0.05, then I reject my null hypothesis. Okay, and if it's greater than 0.05, because again I'm dealing with a 5% significance level, if it's greater than 0.05, then I do not reject my null hypothesis. All right, a lot of words. Let's go through an example. Let's talk about a survey that was given to 100 men and women to see whether they prefer to own a dog or a cat. So here's the contingency table. 42 men like dogs, 10 men like cats, 9 females liked dogs, and 39 women liked cats, and there's the totals there. Okay, so we want a 5% significance level. We need to test whether a person's pet preference depends on their gender. Okay, so my null hypothesis is going to say that gender and pet preference are independent. That's what my null hypothesis says, is that the two variables are independent. H1 is going to be that they are not independent. That's my alternate hypothesis. I have 1 degree of freedom because just the data without the totals makes up a 2 by 2 table. 2 minus 1 is 1. The other 2 minus 1 is 1. So I have 1 times 1, which is 1 degree of freedom. My significance level is 5%. I was given that. So if I look up that value in the table that I got a while ago, that is a critical value of 3.8415. So my chi-squared, I need to compare my chi-squared to that amount. So I'm going to reject my null hypothesis if I calculate my chi-squared and I get something that's bigger than that 3.8415. So I actually do a chi-squared on my calculator and I get 38.4. That is way bigger than 3.8415. So I reject my null hypothesis. Okay. Also, if I look at the calculator after I did the exact same chi-squared test, I get a p-value that is 5.7 times 10 to the negative 10. So imagine that decimal place being moved 10 places to the left. So 0.000, a bunch of zeros, and then 5.7. That is way less than 0.05, and that's more evidence to reject my null hypothesis. So we're going to go over this in quite a lot of detail tomorrow. It's a bit of work, something I had never seen before. Learning about this lesson just this past summer, so it's probably going to be new to you as well. So it wouldn't hurt for us to do as much practice as possible. If you have any questions, please let me know, and I will see you tomorrow.